Good morning, class. Today I would like to complete the next practice problem with you. It's titled The Boat Propeller. So what I want to do is read the problem, and I'm going to underline important information, and I'm going to generate a column of knowns, and then I'm going to work through the problem with you. So let's go ahead and get started. A boat's propeller has a rotational moment of inertia of 4 kilogram meters squared. After a constant torque is applied for 8 seconds, the propeller's angular velocity changes from a clockwise 6 radians per second to a counterclockwise 6 radians per second. Calculate the net torque applied to the propeller. So we need to calculate the net torque, okay? Now what I've done, I've already drawn a picture. Well, started to draw the picture of the initial and the final situation. So for the initial angular velocity, it is clockwise. And we know that angular velocity is a vector, so angular velocity describes both magnitude and direction. And we know that a clockwise rotation is negative. So right here, initial angular velocity is 6 radians per second, okay? But since it's going clockwise, it's going to be negative. So in my known column, omega sub I is going to be negative 6 radians per second. In the final situation, so the torque is applied for a time of 8 seconds, and it reverses the direction of the propeller right here, omega sub F, so the final angular velocity of the propeller, 6 radians per second. Now this is counterclockwise, and we know a counterclockwise rotation is positive. So final angular velocity is 6 radians per second, and that's going to be positive. We know some other things here. So the moment of inertia, identified by capital I, is 4 kilogram meters squared. And also we have a time interval of applied torque, so delta T is 8 seconds. Now, in order for us to calculate the net torque applied to the propeller, we're going to have to use the angular impulse, angular momentum theorem. So this tells us that an angular impulse applied to an object will result in a change in the object's angular momentum. So I'll go ahead and write that on the board here. So angular impulse is going to be equal to delta L. Now remember, the capital Greek letter delta represents change in. Capital L is the object's angular momentum. So what we have on the right side of the equal sign is the final angular momentum minus the initial angular momentum, okay? So angular impulse is identified by net torque applied to the object multiplied by the time interval of the net torque. This is going to be equal to the object's moment of inertia multiplied by the final angular velocity minus the initial angular momentum, which is the moment of inertia of the object multiplied by the initial velocity. Okay, so what we have here, we should go ahead and factor out our moment of inertia. So on the right-hand side of the equal sign, when I factor out moment of inertia, this is going to be multiplied by the final angular velocity minus the initial angular velocity. Now on the left-hand side of the equal sign, our unknown in the problem is net torque applied to the boat propeller. We know delta T, so we need to isolate the net torque. I'm going to do that by dividing both sides of the equal sign by delta T. So on the left side of the equal sign, our time interval of applied torque, that cancels. Okay, now we can fill in some values here. Our moment of inertia for the boat propeller is 4 kilogram meters squared. Our final angular velocity, okay, let's look in our column of knowns here. So we have a positive 6 radians per second. And we're going to subtract our initial angular velocity. Well, our initial angular velocity is negative 6 radians per second. And we're going to divide by a time of 8 seconds. Now let's go ahead and take care of the numerator first. So 6 minus a negative 6, we have two negatives here, so that's going to turn into a plus sign. So 6 radians per second plus 6 radians per second is going to be 12 radians per second. And we're going to multiply this by the 4 kilogram meters squared. This is the moment of inertia for the boat propeller. So 12 times 4 is 48. So in my numerator, I have 48. And we're not going to transfer our angle measure here of radians. So what we have is kilogram meters squared per second. And we're going to divide this by 8 seconds. So let's talk about the numerical value first. 48 divided by 8 is 6. And I need to erase here for some room. Let's take a look at our units right now. So remember, whenever we divide fractions, it's like multiplying by the inverse of the denominator. In our denominator, we have seconds, which algebraically can be written seconds over 1. So when I multiply my units in the numerator by the inverse of the denominator, what we have here is kilogram meters squared per second times the inverse of the denominator, which is 1 over seconds. Okay, so multiplying fractions, we're just going to multiply straight across. So in my numerator, I have kilogram meters squared per seconds times seconds is seconds squared. Now we're not finished here because we need to factor out one of the meters, okay? So when I factor out one of the meters, this is going to equal a kilogram meter per second squared times a meter, because we factored a meter out. And we know that a kilogram meter per second squared is a Newton. So what we have is Newton times meter. And we know that this is the correct unit for torque in the metric system. So our answer is 6 Newton meters. Okay, so I hope I have helped you with the boat propeller problem. If you have any questions, please send me an email, and I hope you have a wonderful day.